I look to the sky where an elephant's eye.
CH1501 Unit 3A Atomic Structure and Wave Mechanics. Today we will going to discuss regarding uncertainty principle of Heisenberg and Schrodinger wave equation. I am Dr. Devang Pandya from Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Today points to discuss, we are going to discuss Heisenberg's uncertainty principle, Schrodinger wave equation, and normalized and orthogonal wave function. Let's begin with Heisenberg's uncertainty principle. A direct consequence of dual behavior of matter as well as radiation led to Heisenberg uncertainty principle. This principle states that the position and momentum of a particle cannot be simultaneously measured with arbitrarily high precision. To measure the position and the momentum of a particular particle, we must see the particle. And so, it should be shine on some light of wavelength lambda. We can see each other because the radiation will fall on us, reflect back to the person's eyes, and it create an image, and therefore we can see. So radiation is a medium to see an object, and similarly to see a particle we need to use radiation. Again, there is a limit to resolve the power of the light used to see the particle given by the wavelength of light used. This gives an uncertainty in the particle's position, that is delta x. Also, we can consider a light as a composite of photon, or we can say having a wave nature as well as particle nature, matter nature. The light when striking the particle could give up some of or maybe all of its momentum, its kinetic energy to the particle. Thus, there is an uncertainty in the momentum of the particle delta p. Combining the two effects, we can write that delta x, the position uncertainty, and delta px, that is a momentum on direction x of the particle, is greater than or is equal to h upon 4 pi. From this we can say that in principle there is a limitation to measure accurately and simultaneously the position and momentum of a particle. If one tries to measure the position more accurately by using light of a short wavelength, which is never possible, but again if we think that we have a radiation with a shorter wavelength, then uncertainty in momentum will increase. Whereas in order to reduce the uncertainty in momentum, if one uses light with a longer wavelength, then the uncertainty in position will be high. Thus, one cannot know or reduce both uncertainties to zero simultaneously. This is a direct consequence of the wave-particle duality nature of a particle, which already we have discussed in the previous lecture about de Broglie's postulate. Werner Heisenberg won a physics Nobel in 1932 for this invention, and already I have said in my previous class that Heisenberg is a German chemist, and he was the coordinator, or we can say head of atom bomb committee during the Second World War, and he has given this uncertainty principle. Another form of Heisenberg uncertainty principle. Another form of Heisenberg uncertainty principle represented as delta E, that is the energy difference, and delta T, that is the time difference, greater than or is equal to h upon 4 pi, where delta E is the energy difference between two states and delta T refers to the lifetime of energy state. This form of Heisenberg uncertainty principle is used in spectroscopy to explain the relation between lifetimes of states and widths of lines. When the electron is in 1s state of hydrogen atom, if it is not disturbed, then delta T is infinitely high and delta is going to be 0. The energy state is very precisely defined over here. Now to understand this uncertainty, I have little examples to discuss with you people. Here you can see that one fellow is running, and if somebody is standing very patiently, and if this fellow who is running fast and going to push that fellow, or again you can think that if somebody is moving in a circular pathway like this one, and if somebody is coming behind with high speed, will going to push that fellow, what happen? If they collide, we can reduce the exactness of position, but after the collision, the fellow who is moving with a steady pace surrounding in a circular pathway will either flung out of the circle, or maybe its speed is going to be either double or maybe multiple. So that is one example, that if somebody will going to hit. Here you can see the example, one marble is there. If we are going to hit the other marble, the position will get distorted, the velocity get distorted as well. Another example is of carom. You can see here the fellow is striking with a striker to the object. When he hit the object, the kinetic energy of the striker reduce and the object velocity get increased. So when we minimize the position's uncertainty, momentum's uncertainty get increases. Here also the same marble concept is there, where you can see that one object is coming, and when it going to hit or collide with this object, it will pass on its kinetic energy to it, and it will stop, and the another kinetic energy get increases. So when we try to precisely measure the position, the momentum is going to be uncertain. Similarly, that happened with this one. When we apply energy to the moving electrons, when energy will collide, the particles, if we will reduce the uncertainty in the position, if this collision is successful, we can reduce the uncertainty in the position, we can measure the position, but the momentum, or maybe the electron will come out of the trajectory path, and that way we cannot measure the momentum. So here it is proved that the momentum as well as the exactness of the place of a moving microscopic particle is impossible to measure simultaneously. Some other example you can see, it will going to give you more idea. It will going to impose a radiation to see the position of electron. What happened here, you can see that this is a photon having wave nature as well as particle nature, and it is going to collide with the electron. So when we going to measure the position of the particle, the momentum get increased and it will come out of the trajectory path. So that you can see over here, the movement of electron is in the wavy nature here. The uncertainty principle of Heisenberg. Let's see what happened here. The position and momentum cannot be known simultaneously. To explain this, I have one emitter that is going to emit the electron, the other one is the receptor. Momentum can be measured as mass into velocity. Velocity is given distance by time. Here we have time. This one is the distance. Now the electron will travel the distance with time. We can measure the velocity and momentum as well as this position. But to see this electron, when we are going to use some radiation, electromagnetic radiation like light or photon. Now what happens is it also have a particle nature. Electron is already have a particle nature. When they collide, trajectory will get changed. It will get a different position. So if we are going to measure the momentum, the position will get different. So that is what uncertainty what Heisenberg wants to tell us. When the photon is necessary to know the position, its the electron changes its direction and distance away and cannot be affected. Position and momentum cannot be known simultaneously. Let's see the significance of this uncertainty principle. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for microscopic objects. In case of microscopic objects, such as electron, the interaction of the striking photon of light with the particle may cause appreciable displacement of the particle and its normal path. As a result of this, the particle undergo a considerable
in our
change.
daily life. This principle has no significance. This is because we come across only large objects, that is, the objects which we can observe with naked eye without altering their motion. The position and velocity of these objects can be determined accurately because in these cases, during the interaction between the object and the measuring device, the change in the position and velocity are negligible.
Mathematical expression for the principle. If delta x is going to represent the error or uncertainty in the measurement of the position and delta p represent the uncertainty in the measurement of the momentum of a subatomic particle like electron, proton, neutron, hydrogen atom, then according to this principle, these two quantities are related as delta x into delta p. Uncertainty in position and uncertainty in momentum is greater than or is equal to h upon 2 pi. Now in certain case you may found h upon 4 pi. In certain references it would be written as h upon 2 pi. That is the uncertainty relation where h is the Planck constant and the sign greater than or is equal to indicates equal to or greater than. And in our reference which we have used, that is inorganic chemistry by Stoley, the value is given h upon 2 pi. The relation given above is called uncertainty relation. From this relation, it is evident that if delta x is small, that means if the position of a particle is measured accurately with accuracy, delta p will be large. The momentum will be measured less accurately or with less accuracy and vice versa. Thus, if one quantity is measured accurately, the other quantity is measured less accurately. This, in other words, means that certainly of the determination of one quantity introduce uncertainty for the determination of the other quantity. This fact can also be shown as follows. If position of a particle is measured accurately, that is delta x should be equal to 0 and hence delta p is equal to h upon 2 pi into delta pi is equal to h upon 2 pi delta pi. There is no variation in pi value, that is why it is 0, and 0 into 2 pi is equal to 0, so h upon 0 is equal to infinity. So there the momentum is going to be infinitely high, means that the error in the determination of the momentum is infinitely high. The measurement of the momentum of a particle cannot be made. In other words, the simultaneous measurement of position and momentum with absolute accuracy is impossible. In m is if m is the rest mass of the particle and is the uncertainty in the measurement of its velocity, then delta p is equal to delta v into m, On putting delta P is equal to delta V into M in the uncertainty relation, we get another form of uncertainty relation and vice versa. That is delta X into delta V into M is greater than or is equal to H upon 2 pi, or delta X into delta V, that is uncertainty in position and uncertainty in velocity, is greater than or is equal to H upon 2 pi M. Now Heisenberg's uncertainty principle as applied to large and small particle. It will reveal the limitation of uncertainty principle of Heisenberg. Whether Heisenberg's uncertainty principle is applicable to large particles like a ball or a small particle such as electron, proton, neutron, hydrogen atom like subatomic microscopic moving particle can be known calculating the value of delta X or delta V of these particles from the uncertainty relation which is given as delta X into delta V greater than or is equal to H upon 2 pi M, and then comparing these values with the velocity or size diameter of the particle respectively. For example, if the calculated value of delta V for a given particle is very small compared to the velocity of that particle, uncertainty principle is meaningful for that particle. On the other hand, if the value of delta V for a given particle is quite large compared to the velocity of that particle, this principle is meaningless for that particular particle. Similarly, the value of delta X can be compared to the size diameter of the particle, and applicability of the particle of the principle to the particle can be predicted. Well, we have bifurcated this limitation of uncertainty principle for the particle in two parts. One where the delta V for a large particle, then what happened? Let us consider a large particle like a ball of a mass of 1 gram. 1 gram, that means 1 into 10 raised to minus 3 kilogram, whose uncertainty in position is equal to 10 raised to minus 10 m. Then delta V is equal to H upon 2 pi m delta X is equal to 6.624 into 10 raised to minus 34 joule into second divided by 2 into pi value, that is 3.14, into m, that is 10 raised to minus 10 raised to minus 3 kilogram, and uncertainty delta X which is given 10 raised to minus 10 m. This calculation will gives us value 1.05547 into 10 raised to minus 21 meter second inverse. This value of uncertainty in velocity delta V is very small, and hence it is negligible to the unusual velocity of the ball. Thus, to talk about the trajectory of a large particle like a ball having such a small value of delta V is meaningful. In a similar way, if the value of uncertainty in position delta X is calculated for a large particles, it is found to be very small, and hence it is negligible compared to the size diameter of the particle. Consequently, in the case of large particles, we can talk about the position and velocity simultaneously. Now let us consider the small particles and its delta V value. Let us consider an electron in hydrogen atom with the mass 9.108 into 10 raised to minus 31 kg, whose uncertainty in position, that is delta X, is equal to 10 raised to minus 10 meter. So the uncertainty in position we have kept quite similar, just a weight and a diameter of the particle get changed. So delta V is equal to H upon 2 pi delta X into M is equal to 6.624 into 10 raised to minus 34 joule into second divided by, that is the value of Planck constant, divided by 2, that is 2, into pi, that is 3.14, into delta X, that is 10 raised to minus 10 meter, into M, that is 9.108 into 10 raised to minus 31 kg, and this calculation when we do will get 11.580 into 10 raised to 5 meter second inverse. This value of uncertainty in velocity is quite large compared to the velocity of the electron. Velocity of an electron would be 1.2 into 10 raised to 5 meter second inverse. Thus, to talk about the trajectory of a small particle like electron having such a large value of delta V is meaningful. In a similar manner, if the value of delta x is determined for a small particle, it is found to be very large compared to the size diameter of the particle. The above description clearly shows that uncertainty principle is applicable only for the small particle, that is moving microscopic particles which have wave as well as particle nature, such as electron, proton, neutron, hydrogen atom, etc., and has no significance for large particle or macroscopic particle like cricketing ball, like any big object like planets, etc. Now these are the two numericals for your practice. You can do it at home. You need to calculate in SI unit, calculate the uncertainty in the position of delta x of an electron. If delta V is given as 0.1%, take the velocity of electron as 2.2 into 10 raised to 6. This is subscript. It should be superscript. You need to keep it into mind. This is 10 raised to 6 meter second inverse. Mass of electron would be 9.1 into 10 raised to minus 31 kg, and Planck constant, do not consider 6.626. Here you need to consider 6.6 only. 6.6 into 10 raised to minus 31 joule into second, and then after calculation you need to comment on your result. And second example is in SI unit. You need to calculate a microscope using suitable photons is employed to locate an electron in an atom with a distance of 0.1 angstrom. What is the uncertainty involved in the measurement of velocity? Here we are measuring the uncertainty in position, and here this example where we need to measure the uncertainty of velocity. Sometimes uncertainty of momentum would be asked as well. So these are certain numericals for your practice. Now, what is Schrodinger wave equation? Schrodinger wave equation is a mathematical expression describing the energy and the position of electron in space. Because after the uncertainty principle and de Broglie's matter wave concept, all atomic model got limitation in one way or other way, and nobody can clearly explain the behavior of electron in the atom. Position of proton and neutrons are well defined, but the position of electron is undefined. And taking into account the matter wave nature of the electron inside an atom, when this kind of calculation has been done, and it should be represented in the mathematical expression form, which is considered as Schrodinger wave equation. It is based on three considerations. Number one, classical plane wave equation. Number two, Broglie's hypothesis of matter wave. And number three, conservation of energy. So on the basis of these 3 points, Erwin Schrodinger has given us a mathematical expression to define the energy and position of electron in space, to define the atomic structure in proper way. Schrodinger equation gives us a detailed account of the form of the wave functions or probability waves that control the motion of some smaller particles. The equation also describes how these waves are influenced by external factors. Moreover, the equation makes use of energy conservation concept that offers details about the behavior of electron that is attached to the nucleus. Besides, by calculating the Schrodinger equation, we obtain value of psi and psi square, which help us to determine the quantum numbers as well as the orientation and shape of orbitals where electrons are found in a molecule or an atom. And that is how we are able to define the atomic structure in a better perspective. Now, wave mechanical model of atom and the Schrodinger wave equation. Although Bohr's concept of strictly defined orbits, that is stationary orbit round the nucleus, was abandoned when de Broglie's concept of wave nature of electron and uncertainty principle of Heisenberg, these two, or we can say the idea of uncertainty of position of electron in atom or space in atom came in light. Yet Bohr's concept of the existence of stationary energy state, energy levels around the nucleus was retained in order to explain the atomic spectra. It means Bohr theory is not completely ruled out, but the concept of stationary instead of stationary orbital, the discussion of stationary energy state is going to be retained from the Bohr's theory. Now, after the failure of Bohr atomic model, the scientists were in search of a new model that could combine the following three concepts and explain the movement of electron in an atom. Wave nature of the electron, that is given by de Broglie's concept. The idea of the uncertain of the position of the electron in an atom, that is Heisenberg's uncertainty principle, and the idea of stationary energy levels instead of orbital stationary energy level that is fixed around nucleus, surrounding nucleus, that is given in the Bohr's postulate. Keeping that three rules into mind, a new concept has been designed, the atomic model that takes into account the wave and particle nature of electron is referred to as wave mechanical model of an atom. And because it has particle nature and it possesses some sort of energy, so quanta word is going to associate with this one. And with this point, quantum mechanics and wave mechanics combine together when you are going to address the atomic structure. In 1926, Erwin Schrodinger, an Austrian physicist, developed the wave mechanical model of the atom. In this model, he visualized the atom as a positively charged nucleus surrounded by a standing or stationary electron wave which extend round the nucleus in Bohr's circular orbits. Thus, this model described the electron as a three-dimensional wave in electronic field of positively charged nucleus. Schrodinger proposed that if the electron has wave-like nature, it should obey the same equation of motion as all the other non-type of wave obey. On the basis of this simple idea, he derived an equation which described the wave motion of an electron wave along any of the three axes, the x, y, and z axis, and is called Schrodinger wave equation. Moreover, Schrodinger wave equation is based on one of the scientists and who has identified or given some calculation or 100 equation for an imaginary planet on imaginary waves and on imaginary planet. Later we will discuss on that one. So for that, what Schrodinger has done, Schrodinger has taken a firm support and bind a string to it, and he has vibrated a string. Suppose we have a firm support over here and consider that this is a string, and if we are going to vibrate it, we know that this kind of wave is going to generate with the string. For that wave, simple harmonic motion for this kind of wave which is created with a firm support and a thin thread. When we are going to vibrate, we're going to get this kind of wave, and for that wave Schrodinger has given one equation, that is psi is equal to a sine 2 pi x by lambda, and we have given one number to this equation where psi represent the amplitude of the wave. Amplitude, that means the height, maximum height of the sine and maximum depth of the thorns, that is considered as the amplitude, and that amplitude is represented as psi is equal to a sine 2 pi x by lambda, and that amplitude of the wave is called the wave function. So this is considered as the wave function, and x represent the displacement of the wave or propagation of the wave on x direction. Suppose this one is the x direction, then this wave will propagate on x axis. So x will define that one, and lambda will be the wavelength of this wave, say of the simple thread. And with that Schrodinger has compared electronic wave later on, but this psi is an amplitude and it is defined as a sine 2 pi x by lambda, where x is the direction of displacement of the wave, lambda is the wavelength, 2 and pi they are the constant, and a is the constant, normalization constant of the wave function. We are going to discuss normalization later on, and psi will represent the wave function. On differentiating the equation 1 with respect to x, we are going to get this one, d psi by dx is equal to a cos 2 pi x by lambda into 2 pi by lambda, or we can say d psi by dx, where we are going to put the value of psi as a sine 2 pi x by lambda, and if we are going to differentiate it, simple differentiation, it will going to give us this value, a cos 2 pi x by lambda into 2 pi by lambda, or we can represent this equation as d psi by dx is equal to 2 pi a, 2 pi into a, this one 2 pi into a upon lambda into cos 2 pi x by lambda, and that we have numbered 2. By differentiating this equation 2, we get, so double differentiation, this one is single, now double differentiating this equation number 2, so d square psi by dx square is equal to 2 pi a by lambda into minus sine 2 pi x by lambda into 2 pi by lambda, and this 2 pi and 2 pi, when we are going to multiply, it's going to give us 4 pi square a by lambda into lambda, that is lambda square, into minus sine, minus is missing over here, you need to keep it into mind, minus sine 2 pi x by lambda is equal to minus 4 pi square by lambda square. Now we will going to keep this a and sine 2 pi x by lambda together, and this is like a wave function. So here instead of a sine 2 pi x by lambda, we can put the value of psi over here. So we are going to get this square psi by dx square as minus you need to put here by mistake, typological mistake, minus is not there, minus is not here as well, minus is not here, but in all these three value you need to put minus 4 pi square upon lambda square into psi. When this value will going to keep this side of this double bond, we're going to get this square psi by dx square, the minus value now comes to this side as plus 4 pi square psi by lambda square is equal to 0, and you need to number it as 3. So this is the derivation of Schrodinger wave equation. Now when we get that simple Schrodinger wave equation, when you see here, this is a simple Schrodinger equation, and it is also considered as a simple form of Schrodinger, simplest form of Schrodinger equation, if somebody will ask you in any MCQ or any other thing. Now this is the classical wave equation which describes the wave motion of a particular vibrating along with the x-axis. This represent what? These wave functions is a wave equation is going to describe the wave motion of any particular particle vibrating along x-axis, like this one vibrating along x-axis. With the confirmation of the idea that electron in an atom is described as a standing wave round the nucleus, the classical wave equation, that is equation 3, which describes the wave motion of any particle vibrating along x-axis, should be applicable to the standing wave of an electron. We have seen in Bohr's theory the total energy of an electron is the sum of the kinetic energy and the potential energy. So total energy is the sum of kinetic energy and potential energy. Kinetic energy is represented as half mv square, plus potential energy is represented as v. You need to branch this equation as 4. In this equation 4, m is the mass of electron, v is the velocity of electron, and mass and velocity square and its half value that represent the kinetic energy, and the velocity with which electron is moving, that is represented by v, and this big V represent the potential energy. Now if we will going to study the de Broglie's concept of wavelength lambda. De Broglie's equation says that lambda is equal to h by mv, or we can say mv is equal to h by lambda. Now if we're going to take the square of this equation, we're going to get m square v square is equal to h square by lambda square. Or if we're going to put that value over here somewhere, then 1/2, if we're going to take the half value of this m square v square, we can write half m square v square is equal to h square upon 2 lambda square. That means we have multiplied this equation by half both the side. So both the side, when we multiply this equation by half, we're going to get half mv square is equal to half h square upon lambda square, or is equal, or it should be represented, if we are going to remove this m, one of the m over here this side, then this one of the m will going to come in this side of the double equal to, then it will go to denominator. So half mv square now can be represented as h square upon 2 lambda square m, and when we number it as 5, and then after we need to put the value of this half mv square from equation 5 in equation 4, we will get E is equal to h square upon 2 lambda square m plus v, or 1 upon lambda square is equal to 2m upon h square into bracket E minus v. Number this equation by 6. Putting the value of 1 upon lambda square, that means this value, from equation 6 into our equation 3, we're going to get d square psi by dx square plus 4 pi square psi x square, this is square, 4 pi square psi into 2m upon lambda square into E minus v is equal to 0. Now when 2 is multiplied with this 4, it is 8 pi square, and we are going to put m there. So this will be represented as d square psi by dx square plus 8 pi square m upon lambda square E minus v psi is equal to 0. Number this equation as 7. And the 7th equation is a Schrodinger wave equation which is propagating on x direction. If we think we need to represent into 3-dimensional form, then it should be written as d square psi by dx square plus d square psi by dy square plus d square psi by dz square is equal to plus, this is plus not equal to, it is a typological mistake, 8 pi square m upon lambda square is into E minus v psi is equal to 0, and branch this equation as 8. Please note, this is not equal to symbol, you need to write plus symbol over here. This is a 3-dimensional Schrodinger wave equation. We need to learn about the simplest form of Schrodinger wave equation that we're going to discuss in our next class. But before that, we need to study the Born interpretation of the wave function psi. Psi has no physical significance, but psi square gives the probability density at a given point. That is told, this information is given by Max Born. According to Max Born, normalized wave function can be represented as integration psi I into psi j star. That this star represent that psi I star is a complex conjugate of psi I. So integration psi I into psi I star, that is its complex conjugate, d tau. Tau represent dx dy dz. That is three-dimensional, three different direction. So integration psi I into psi I star, that is a complex conjugate, d tau is equal to 1. When this integration will going to get 1, it is considered as a normalized wave function. And similarly, if the integration psi j into psi j star, so psi j is a wave function and psi j star is a complex conjugate of psi j, d tau is equal to 1, then that wave function is considered as normalized wave function. So this is the condition of normalization, or this is a condition for a well-behaved wave function. The characteristics of this well-behaved normalized wave function psi can be represented as SCFBN. Now what this SCFBN means? S, that is a single valued, that means the wave which is propagating on any particular direction must have a single value. It must be continuous and doubly differentiable. Third, it should be finite. So you can say the first wording S, C, that is for continuous, F, that is for finite. Propagating wave must have finite value at one position, and it satisfy boundary conditions. It should satisfy boundary conditions. So this satisfy boundary condition. So here you need to color B. So boundary condition, and then last one, it should be normalized, well behaved. And if it is not normalized, by multiplying with any constant, we can normalize this wave function. So in Schrodinger wave equation, you have seen that constant A, that is nothing else but it is a simple normalization constant. Now interpretation of psi, psi square and psi star. As already I have said, wave function has no physical interpretation, no physical significance. If the solution of the wave function psi x, the electron is in the boundary of x plus dx. I already told you that it should follow boundary condition, and its value is indicated as psi square dx, means in a volume of dx, the probability of finding electron can be indicated as psi square. The wave function should accept these four conditions which already I have said. At one point the value must be 1, that is single valued, which already represented in previous slide. The value of psi must be finite, that is there as well. The value of psi for all x's must be continuous, and the value of psi must be normalized. So if any wave function will follow this condition, then it is considered as well-behaved normalized wave function. Now these are the condition of normalized wave function already explained by Max Born. The probability density, psi square indicates the probability density according to Max Born. And I use word probability density. Let me tell you one example. If somebody will ask you when you are in class, or you may be outside somewhere with your friend, and if somebody will ask you in the morning time, where is your mom, then generally you may say, my mom is in my house, she probably cook food for us, or preparing dinner, or lunch for us, because you know that that particular time your mom would be in your house. So the probability of finding your mother would be the kitchen. Kitchen is the right place where you can find your mother. So that indicates the probability density. But it is not necessary that at that point of time she must be in the kitchen. Maybe she outside in the drawing room, she may be outside in the veranda or outside of the house as well to purchase some vegetables or miscellaneous. So but very often that particular time she always been in the kitchen, and you may say that at this point of time my mom would be in the kitchen. So that indicates the probability density. That means that point of time, if you found a particle within the nucleus or surrounding the nucleus from minus infinite to plus infinite, if the probability of finding electron is 100%, then it is considered as normalized, well behaved wave. If due to any reason the value 1 is not going to be obtained, we need to multiply with a normalization constant and it will get the value 1. Then also the wave function is considered as normalized, well behaved wave. So here n would be the normalization constant. Now orthogonal or orthonormal wave function. So there is another condition for orthogonality. For to prove normalization, we required only one function or the function with its complex conjugate. But if we want to prove the orthogonality of the function, we required at least two or more than two wave functions. So suppose if we have two wave functions psi a and psi b, and if we are going to integrate it from minus infinite to plus infinite in the volume of d tau, if this integration value would be 0, where a and b, which are the arbitrary constant for particle a and particle b, and psi a and psi b are the wave function associated with particle a and b, where a and b are not similar, and if their integration result into 0, then there should be orthogonality relation between these two wave functions. So that you need to keep into mind. Orthogonal wave functions are free from each other. They haven't any kind of relation. Now orthonormal set, orthogonality and normalization simultaneously. If we have this value, two wave functions psi and psi b, and if we are taking the integration, if value is 0 in the volume of d tau where a is not equal to b, it is called ortho set. And if in the same condition psi a and psi b from minus infinite to plus infinite in small volume of space, that is d tau, if that value is 1, where a and b are similar, that means a single particle, then it is considered as normal. So this is orthogonality condition, this is normalization condition, together it is known as orthonormal set. And with this I will like to conclude today's performance. Thank you very much for paying attention to this lecture, and this is for you. Keep it into mind, you will be benefited. Thank you very much.